Okay, so in helicopter problems, when it's accelerating forward, the helicopter has to be tilted at some angle. Okay, and when we draw our free body diagram, there's the helicopter. Well, we put the weight going down as normal, as we do normally. Drag's going that way, but the thrust will be an angled force. And so they're giving us the angle, unfortunately, to the perpendicular. So our trig equations are designed for when the angle is taken from the x-axis instead. So you gotta be careful about that. Okay, so this will have an x and y piece. The slant force will have an x and y piece. We'll call that vertical piece thrust y. We'll call the horizontal piece the x component. As before, once you put in the x and y components, you can disregard the slanted force. Okay, because the x and y components will add up to be the slanted force. Okay, so basically just watch out for that angle. Solve for the net force in the x direction. Okay, well, I'm assuming that the thing's accelerating forward. It could be accelerating backwards, but we'll find that out. So D is equal to the drag is at 6,000 newtons. The weight is equal, okay, I didn't give you the mass, I gave you the weight directly, it's 40,000. So first thing they're asking me for is the net force in the x direction. Well, that's kind of unusual, because usually that's the last step. Okay, but we can, since we have acceleration right there, we can do the net force, horizontal net force at least, is m times a. The mass is, well, don't use the weight for the mass. The mass would be 40,000 divided by 10, right? W. So the mass is W equals mg. So the mass is equal to the weight divided by g, or the weight divided by 10. So that would equal 4,000. And then the acceleration is given right here is 4.5 meters per second squared. So that comes out to 18,000 newtons. So that's the net force in the x direction. Now, what about the net force in the vertical direction? Well, it's neither gaining or losing altitude, so the net force in the y direction is 0, because those forces have to be balanced. Okay, let's solve for the x component of the thrust. Okay, well, I know the drag is 6,000, and I also know that the horizontal forces only consist of the drag and the x component of the thrust. And we found that the net force in the x direction is 18,000 newtons. So, how do these two forces, these two horizontal forces, relate to the net force in the x direction? Well, so who's bigger than who? Well, I'm assuming it's accelerating forward. So EFX is equal to THX minus the drag. So 18,000 equals THX, which I'm trying to solve right here, minus 6,000 drag. Therefore, THX is equal to 18 plus 6, which would be 24,000 newtons. Okay, so let's find THY to prevent any vertical acceleration. Okay, so let's look at our picture. Well, THY has to equal the weight. Why? Why does THY have to equal the weight pointing down? Because its balance is saying that it's neither gaining or losing altitude, so its net force in the y direction is 0, like I mentioned over here. So those two forces have to equal each other. So THY, the y component of thrust, has to equal the weight, or else it'd be either losing altitude or gaining altitude. So that equals 40,000. Now, you have THX and THY. You got the x and y components. How do you solve for TH? Well, it's Pythagorean theorem. So basically, TH is the square root of THX squared plus THY squared. And so THX is 24,000. And THY, we just found, is 40,000 squared. Then you take the square of both those and add them, and then square root your answer in this. So calculate that out. You get 46,647. I'm not going to round it. I should, but I'll just take it to the decimal point. Newtons. Finally, solve for the tilt angle. Okay, well, strangely enough, the tilt angle is the angle from the y-axis, as you can see in my diagram. Now, why would that be so? Well, if you look at the picture from positive physics right there on the left, if you have two lines that aren't parallel, okay? Let me just give you this theorem in geometry. And if you take a perpendicular to one of those lines and anywhere on the other line, you take a perpendicular anywhere to that, then where these two lines, where these two perpendiculars meet, like right there, will be the same angle as between the two non-parallel lines. So those two angles will be the same. Now, you don't have to know that rule, But that is explaining why this angle right here is the tilt angle right there. So just memorize. It's the angle from the y-axis. That's the tilt angle. Then you don't have to do all the geometry proof. Okay, so when I'm going to solve for the angle, the tilt angle, really I'm going to have to switch around my trig equations on my equation sheet. So that's no big deal, I hope, for you. So the tilt angle is really, what's the equation for tangent? Tangent of -1. The angle equals tangent -1. The opposite over adjacent, right? Well, the opposite side is really right here. That's THX. And the adjacent side is THY. Adjacent to the angle from the y-axis. So this is backwards from what I usually write on my equation sheet. Theta equals tangent -1 THY over THX. That would be true if the angle's from the x-axis, which I always do, except for these special cases. So just flip it around. Or just use trig, is inverse tangent, and you can see the opposite and adjacent sides of this triangle right here. This triangle right here, you can see that the opposite side is THX and the adjacent side is THY. And so that's why I had to do that. So this would equal tangent -1, inverse tangent of what's THX? I found it up here. Where is it? Right here. 24,000 divided by THY is 40,000. So I can just cross out the 3 zeros on top and bottom. So what's inverse tangent of 24 over 40? So I get 31 degrees being the tilt angle that's shown on that picture. Now, let's look at the ramp kind of problems. Looks very much like the helicopter situation. We got weight pointing straight down. Here, let's do a free body diagram. We got weight straight down, and we got the normal force slanted. But the normal force isn't really causing it to move, like in the helicopter. The helicopter, the lift force, the thrust force, was causing it to move. So we made the thrust force slanted. What we're going to do here is make the x-axis along the plane and the y-axis along the normal force. So what will be slanted in our picture will be the weight. Okay, so pretend I'm taking this cross that I just scribbled and I'm straightening it up. So what we would have is the normal force is pointing up. Let's get this. The weight is angled like that. Okay, look at it. The weight is angled from the y-axis. And right here, okay, I'll do that later, but the weight is right there. The weight has two components, the x and y components. Now there's a slanted force. And so we're just going to draw the x and y components. So we got wx right here. Oops. We got wx right there. And we got we got wx right there and wy right there. We also, usually I will have friction, but this is on a wheel, so there's no friction. Okay, I guess there's no drag. I should have said that. So, kind of makes it a little easier since there's no drag. Now, again, see this angle right here, the ramp angle? That's going to be the same as the angle between the y-axis and the weight. So that'll be the same as this angle right there. Just like it was before, the tilt angle is the same as the angle between the y-axis and the tilted force. But the tilted force is not the normal force, the lift force, it's the weight. So you gotta make that flip. Okay, so there's the angle right there. Okay, so we've set this up. Find the normal force acting on the cart. Well, the normal force has to equal the y component, because the cart is not accelerating into the ramp or off the ramp. Okay, see, it's not lifting or burrowing itself into the ramp. Look at my FBD, free body diagram. There is no vertical according to the ramp. From relative to the ramp, there is no vertical acceleration. So the normal force has to equal the y component of the weight, which they call Wn, which I don't like. Okay, so normal force has to equal the y component of the weight. Now the weight, I don't have to solve for that because it's given right in the picture as 20 newtons. It's given in the picture that positive physics gave you. Now we gotta find the net force. Well, according to my free body diagram, the vertical forces are balanced. So there's no net force in the y direction, according to my FBD. But you can see that the net force horizontally, there's only one unbalanced force. Nothing is balancing the wx out. So according to the ramp, the horizontal force, it's not horizontal in the picture on the left, but according to my free body diagram, the horizontal force is unbalanced. So the net force in the x direction is equal to wx, the x component of the weight. They call that wd, which means the part of the weight that's pushing the cart downward. So the D stands for downward. I don't like that. So that comes, I don't have to calculate that. That's 5 newtons from the picture right there. Find the acceleration of the cart. So F net in the x direction is equal to ma. So net force is 5. The mass is, take the weight. Don't pick the wrong one. Don't pick 20. The weight is 21. and W equals mg. So mass equals W divided by G. So just divide the weight by 10, so you get 2.1 times A. And so A is equal to 5 divided by 2.1 is 2.4 meters per second squared. Okay, find the ramp angle. Okay, so find that angle right there. Again, this is weird because it's from the y-axis. The angle is from the y-axis, so I have to invert what I'm used to with angles from the x-axis. So when I put my equation on the equation sheet, you have to flip it. So this would be tangent of q x over qy instead of what's on my equation sheet. So it'd be wx over wy, which is inverse tangent of 5 over 20, which I get to be 14 degrees. Okay, so this one, you actually have to find the x and y components. So mass is 15. So let's draw on the ramp. Let's draw what we're going to do. There's the weight. There's the normal force. Perpendicular to the surface. No friction or drag. So I'm staying kind of simple still. So let's straighten that out, that free body diagram out. There's the box. Okay, the weight's gonna, there's my y-axis, so normal force is going up. And the weight's tilted over there. There's the angle from the y-axis. That's all I got. So I'm going to do x and y components of the weight. There's wx, and here's wy. So there's my free body diagram. Again, I don't have anything balanced. If there was friction, it would be opposing wx, but I don't have that. What's the weight of the box? Okay, so the weight of the box, mg. Okay, the mass is given as 2.5 times 10, so that's just 25 newtons. Calculate the components of the weight. Okay, wx and wy. Now, be careful because that angle, you gotta realize that the ramp angle is the same as the angle between the y-axis and the slanted force, in this case, the weight. And so the trig equations I give you on the equation sheet only apply if the angles from the x-axis. So we have to do a flip. So this would be wx would be w times, usually cosine theta, but I have to flip it to sine of theta. And wy, which is usually sine of theta, I have to flip it to cosine of theta. Why? Because the angle is from the y-axis. And again, my equations on the equation sheet for trig functions are for the angle from the x-axis. So this would be 25 times sine of 20. So for this one, I get 8.55, so I'll just say 8.6. And for the other one, I get 23.49, so I'll say 23.5 newtons. Okay, what is the normal force acting on the box? Look my free body diagram. There's no, the net force in the y direction is 0, so N has to balance out with the WY, the y component of the box. So we already found that to be 23.5. What is the net force acting on the box? Well, we already said F, the net force in the y direction is 0, but the net force in the x direction, if you look at my diagram, the Wx is unbalanced, so that is the net force. And we already saw that to be 8.6. What is the acceleration of the box? Okay. F net equals ma. We're talking about in the x direction, so the mass is 2.5 times a, and we got 8.6. 8.6 divided by 2.5 is 3.44. So I'll say 3.4 meters per second squared. Okay, so what if you did have friction? Okay, I don't know why that came up. Okay, so what if we have friction? Okay, I don't know if this is static or kinetic friction, but they gave us both coefficients. So draw a free body diagram. Well, let's do it here first. There's the normal force. Here's the weight. And then you got kind of, there's the y-axis. Here's the x-axis. So I'm going to straighten that out. You don't really have to. You can just draw it right here. But this would be the x-axis, this would be the y-axis, and just tilt it if you want to see it. So that would be, this is W, this is WY, this is WX. And we're going to have friction. I don't know if it's static or coefficient. I don't know if it's static or kinetic yet. Okay, so there we go. Find the weight of the block. Okay, that's easy. 5 kilograms. Mass times 10. Acceleration due to gravity. 5 times 10 equals 50. Find the normal force on the block. Okay, normal force on the block is equal to WY. Okay, and WY, okay, be careful. What's the angle? The ramp angle is given, so that should be between the y-axis and the slanted force, which is the weight. Okay, so we got to do a flip. WY is W, the weight, times, usually it's sine of theta, but because the angle's from the y-axis instead of the x-axis, we got to do cosine. So that'd be 50 times cosine of 37. I get 39.9, so I'm going to just say 40 newtons. Okay. Letter D, find the maximum static friction possible. Okay, well, I don't need the picture for that. US is Fs max over N, normal force. So Fs max is equal to mu s times n. So that equals 0.8 times n, normal force, is 40. So that comes out to be 32. 8 times 4 is 32 newtons. Okay, find the component of the weight that pushes the block down the ramp. Okay, so that's Wx, duh. So I already did that. Wx. No, I didn't do it. Okay, so that is the x component, but remember, because the angle's from the y-axis, we gotta flip it as if it was from the y. Weird. So sine of theta. So that'd be 50 sine of 37, which comes out to be 30 degree, 30.09. I'll just say 30 newtons. Side of the block will be sliding down the ramp in this case. Well, okay, so Wx is to the left. Look at the picture. Wx is right there. So how big can F be? Static friction, 32. So basically, you have not hit the threshold to slide. So friction, the static friction, will equal 30 because it has not gone past 30. Wx has not pulled past 32. So it has to equal because it's at rest right there. So no, it's at rest with the friction being 30 newtons because you need to have Wx greater than 32 for it to slide. So acceleration is 0. It's not sliding. Now, if it was Wx was greater than 32, I'd have to subtract the friction from the Wx. Then that would be the net force, and that would equal ma. Then I can solve for A. Ooh, finally. Samantha pulls a 30 kilogram box. Okay, that's the mass right there. Up at 19 degrees. Okay, that's 19 degrees. Coefficient connect. Okay, they just gave me the coefficient. So it's moving. It's moving. So that's the coefficient of kinetic friction. And she's applying 245. So she's applying 245 newtons of pull. But the string's pulling back both directions, right? Over the pulley, it doesn't matter. Pulley just directs the force in the tension in another direction. But these two forces have to equal because they're tension. So tension equals the applied force. So we know this force is 245 newtons. We'll just call that I'll just call that tension. Okay? So this is going to get messy very soon. So let's draw the other forces act down here. The weight goes down. And then the normal force is up. Tension is the blue one. And then we can break the weight into x and y components. I have to make that thicker. Okay, so here's the x, Here's the y component. So that'd be wy and wx. And remember, this is the angle, which would be 19 degrees between the y-axis. So if you want to make that picture cleaner, so I'm going to straighten it up. Okay, remember, that's the x-axis like that, and the y-axis is along the normal force. Oops. Okay, so normal force is like that. The 245, the tension is 245. I don't know what the normal force is. Wx is this way, and wy is that way. I'm not going to draw the weight. The weight's right there, but I don't have to draw it because I just broke it up into x and y axis components. Okay, so I'll draw it anyway. The W is right there. So this angle between the y-axis and the weight is the ramp angle. That's 19 degrees. Now, don't forget, you also have friction. Which way is that block moving? It's moving to the right, up the ramp, right? So the friction has to be down the ramp to the left. So don't forget to put that guy in. So I'll put him in this. So there's friction to the left. Let me squirt that in there. Looks like it's WXF. So I'm just going to draw it like over here so I can draw the friction. Not that it's bigger than WX. It could be. Yeah, it could be easily. Okay, so I got all these forces. Now, ready to go. What's the weight of the box? W equals mg. So the mass is given as what? 30 kilograms, so it's 300 newtons. C, calculate the components of the weight, Wx and Wy. Okay, here we go again. Wx equals W times, usually it's cosine of theta, but the angle's from the y-axis. This is the x-axis. So it's W sine of theta. The other one's W cosine of theta. So 300 times sine, I don't remember. The angle is 19 degrees. So I just calculate those two components. Calculate the friction. Okay, calculate the, wow. Okay, I guess I did these already. I did that already. Calculate the normal force acting on the box. Okay, N equals Wy. And I already found what Wy was. 284. Calculate the friction acting on the box. Well, I don't look at the free body diagram. I use the coefficient of friction. Mu equals F over N. F equals mu N. So that equals what? 0.40 times 284. Don't use the weight as the normal force. Okay, so 0.4 times 284. I get 113.6, so 114 newtons. Calculate the net force, not the normal force. I already did the normal force, so the net force in the x direction being along the ramp, is equal to ma, but I don't have a, so it equals, look my diagram. Okay, be careful. Wx, let's fill this in now. Wx, where is it? Is 98. Okay, that's 98. The friction we just found to be 114. So that's 114. And the tension is 245. So using that picture, just using the X components, the horizontal forces, we can see 245. Let's see. Let's just assume that T is bigger. So let's just write this. 245 minus 98, because it's going the opposite direction, minus 114. So basically, and write it, T minus Wx minus F. T minus Wx minus friction. That's what my net force in the X direction is. So 245 minus 98 minus 114 gives me 33. That's the net force. So the acceleration of the box is ma. So that would be the mass is 30 times a, 33. So the acceleration is 33 divided by 30 is 1.1 meters per second squared. Phew. Okay, so this is the end of test 2B material. So, and this would help you to do the positive physics number 9.